In the last video, we were working with piecewise functions, and we saw the graph of a piecewise function, and from that graph we wrote its formula. And so now I want to reverse that process. Here in this next problem, we're given the formula for a piecewise function, and we just want to sketch its graph. So we have a formula f of x equals 2x plus 1 if x is less or equal to 1, f of x equals x if x is greater than 1. There's more than one way to do this, but maybe the easiest way is just to make a table of values. And I guess since we have two different rules, we might like to have two different tables. Let's start with a table for 2x plus 1, and then we'll make a table where y is just equal to x. Now, look at this first table. What values for x should we put into this table? Shouldn't we put in numbers that are less than or equal to 1? Like 1, 0, -1, -2. And then we can just find y for each of these inputs. So 2 times 1 plus 1 is 3, and then 1, and then -1, and then -3. And then we can just plot these points. Plot the point at 1, 3. Plot the point at 0, 1. -1, -1. And -2, -3. Notice these points fall on a line, as we would expect. You can also look at the graph and you can see that the y-intercept is right where it should be at y equals 1. You can also check that the slope from each point to the next is 2, just as it should be. And so then we can draw the line. And of course, we want to draw the line from x equals 1, back to the left. Okay, and then the next rule is y equals x. And so what values should we put in for x this time? Well, the restriction says x is greater than 1. So sometimes students say, well, let's start with 2, and then 3, and then 4. But you know, you should really have 1 as well. Do you know what happens when x is equal to 1? You get a hole. You get a hole. So we need all the values that are greater than 1. So that's not just 2, but that's also 1.5 and 1.1 and 1.01 and so on. So we need to show where that hole is so that we can show all of the points that are right beside it. Okay, so when x is 1, y is 1. When x is 2, y is 2, and so on. And then again, really important for this first point at 1, 1, we need to make sure that we draw a hole there. And then the point at 2, 2, and 3, 3, and 4, 4. We can take our ruler and draw out to the left of out to the right from x equals 1. And there's our graph. Notice that y equals x is also a line. It has a slope of 1. We can see that the slope is correct if we go from point to point on that line. You know, there's a y-intercept at 0, and we can verify that if this line extended back to the left, it would pass through the y-intercept at 0, 0, and it would. So there's our graph. Okay, let's just do one more of these. This might be a great time for you to pause the video and try to do it yourself. Make a couple tables and plot the points and see what you get. Okay, so the first table would be x and y equals x cubed plus 5. And we should use that table whenever x is less than 0. So we need to start at 0, where there will likely be a hole, although I guess it's not guaranteed yet. And then -1 and -2 and -3. And the y values would be 5. And then what is that? -1 cubed is -1 plus 5 is 4. And then that would be -8 plus 5 is -3. And -27 plus 5 is -22. So at 0, 5, we can go ahead and draw the hole. -1, 4, we can plot a point. -2, -3, we can plot another point. And then this is a smooth curve. This curve looks very similar to the graph of y equals x cubed, except for two things. First of all, we cut off the right-hand side of the graph. We only have the left side because of the domain restriction, because of the interval x is less than 0. And then the other thing is that the graph of x cubed is shifted up 5 units. That's what the plus 5 does. Okay, let's go ahead and make another table. Let's do x and y equals -x squared. And we're going to use that rule whenever x is greater or equal to 0. So 0, 1, 2, 3. And so I guess we have to be just a little bit careful here. You know, what's getting squared here is just the x value. The negative doesn't get squared. If it were getting squared, then -x would have to be in parentheses. So we're going to square 1 and put a negative sign in front of it. We're going to square 2 and put a negative sign in front of it. And the parentheses aren't necessary. I put those there for emphasis. This is just as good. -3 squared doesn't mean square -3. It means square 3 and then put a negative in front of it. Okay, so we can go ahead and plot those points. Since the interval is x greater or equal to 0, we'll start with a closed circle at 0, 0, and then 1, -1, and 2, -4, and 3, -9 is just off the graph. This section of the graph looks very similar to the graph of y equals x squared, except for two big differences. Number one, we only have the right-hand side of x squared, and then the other big change is that instead of the parabola shooting up, now it shoots down. We'll see that that's called a reflection, and we'll see that in the next section. But for now, our graph is complete, and we finished section 2.6.